Welcome to Mass Transfer Operations lecture series.
An example for a mass transfer operation is the transfer of ammonia from gaseous phase into water. Here what you see is a glass bowl filled with water. A gaseous mixture of ammonia and air is bubbled through water. So let us take a closer look at the bubble and let's see what is inside the bubble. As you see in screen, each bubble is carrying many molecules of ammonia. So you can see the molecules of ammonia trapped inside the gas bubbles. Slowly, the ammonia molecules will travel through the interface into the liquid, that is water, surrounding the bubble. So you have seen that initially there was no ammonia molecule in the liquid. So now the transfer of ammonia molecules from the gas bubble into the liquid surrounding it until equilibrium is reached can be called as diffusion. And this is how the mass transfer or transfer of mass take place on a molecular scale. So molecular diffusion is the movement of individual molecules through a substance by virtue of their thermal energy. So what you see here is a trajectory of a molecule. So since I've told you the moment is due to thermal energy, let's recall kinetic theory, which states that molecules travel in a straight line with a uniform velocity until it will collide with another molecules. So what you see here is, let's say the molecule is starting from this particular point, so it moves in a straight line until it is hit by another molecules, thereby changing its direction and the value of its velocity. So this process continues and the molecules is continuously in a random motion inside the medium. So what you see is the random motion of the molecules. They collide with each other, they change their direction, and the magnitude of velocity also changes. In reality, the process of diffusion mass transfer is extremely slow. So what can we do to increase the rate of diffusion? A process called eddy diffusion or turbulent diffusion is the answer. So diffusion of molecules as a result of mechanical stirring and convective movement of fluids is known as eddy diffusion. So if we provide mechanical stirring, large chunks of eddies or turbulent currents will be formed inside the vessel, which will distribute the molecules uniformly at a faster rates and equilibrium will be reached quickly. I'll demonstrate the difference between eddy diffusion and molecular diffusion with the help of an experiment. Here you see two glasses filled completely with pure water. Let us add 2 drops of ink to the glass. So the ink slowly starts distributing into the water. So what you see here is molecular diffusion, because though no mechanical forces are applied, but very slowly the ink molecules of ink is distributing themselves in the medium liquid. So if we can provide some external stirring, if we can increase the rate of diffusion by stirring, the process can be called as eddy diffusion. So if you take a spoon and stir the mixture properly, the molecules will quickly distribute themselves into the medium and a uniform concentration or uniform color will be obtained. This process is called eddy diffusion. So now we can define mass transfer. So mass transfer is a transfer of a component in a mixture from a region where its concentration is high to region where its concentration is low. So this was visible in all the experiments that I have shown you right from the ammonia transfer. The concentration of ammonia was high inside the bubble, and the molecules of ammonia was moving into the liquid where its concentration is low. So the transfer is occurring from a region where the component concentration is high to a region where its concentration is low. So let us identify the driving force for mass transfer. The driving force required for mass transfer is concentration difference. I'll discuss more regarding this later, but for the time being, learn it like this. The driving force required for mass transfer is concentration difference, and transfer will occur from a region of higher concentration to a region of low concentration. Okay, I mean, this is actually analogous to water flow. So water will always flow from a region of high potential to region of low potential energy. So we need to actually find out the rate at which the transfer take place. What we are interested is to find the rate of mass transfer. So we identified the driving forces concentration difference. So let us see what are the quantities that is required to find the rate of mass transfer. So primarily concentration should be known. So the concentration of the component is required. We also need to know the velocity at which component moves. So in all the demonstrations, you see the molecules are in constant motion. So we need to know two things primarily: concentration of the component and also the velocity at which that component moves. And the transfer will also depend on the area available. If the area available is more, then the molecules are free to move because of the larger surface area available, on the rate will be more. And also it will also depend on the distance the components need to travel. So if it have to travel a longer distance, the rate will be low because the energy is required to travel a longer distance and something like that. So we have identified four factors that we need to know to determine the rate of mass transfer. And also we should familiarize with the unit of mass transfer. Since it's a transfer, we need to standardize a unit which helps us to which will help us to know the quantity or the amount that is getting transferred, and the rate of the mass transfer will be expressed as moles or mass transferred per unit area per unit time. For the time being, just try to remember this. I'll get into details of this. So now I will introduce certain terms which is required to quantify mass transfer. I'll start with mass concentration. Like I said, the concentration of the component should be known. So let us discuss the different ways in which we can represent concentration. So let us take a vessel of non volume. Let's say 1 liter is the capacity of this vessel, and I have three different types of molecules inside the vessel. See molecules A, which is represented by blue, molecules B represented by green, and molecule C represented by red. So all these molecules are in constant motion. I need to calculate the mass transfer rate of individual components. So first thing is I should know the concentration of individual component. Let's represent mass concentration as rho A, where A suffix represents the A molecules here. Here mass concentration is equal to mass of A by total volume of the mixture. So total volume of this mixture will be the volume of the container, since these are gas molecules, and mass of A means the mass of all the A molecules together. Let's say if I somehow manage to separate these A molecules and I'm able to take the mass, that mass is what I'm talking here. So mass concentration rho A is equal to mass of A by total volume of mixture. So similarly, what will be mass concentration of B, rho B? It will be mass of B by total volume of the mixture. So in a mixture there will be many components. So generally we can represent it as rho I. So I represents the component. It can be A, B, C, or anything that we give. And the unit of mass concentration is kilogram per meter cube. Remember, this kilogram corresponding to mass of the component, and meter cube represents the total volume of the mixture. So since we have many components, what will be total mass concentration? So total mass concentration rho is equal to rho A plus rho B plus rho C. That is sum of the mass concentration of all the components present in mixture. And I can write this as sigma I is equal to 1 to n rho I. So this implies rho I, rho A plus rho B plus rho C. So another quantity we required is mass fraction. So you have learned about mass fraction earlier also. The same thing. Mass fraction is represented as small w A. Here A represents the mass fraction of component A is equal to rho A by rho. Rho A means mass concentration of component A. Rho means total mass concentration, that is rho A plus rho B plus rho C. So generalizing, we can write Wi. I represents either A, B, or C, which is equal to rho I by rho. This you can, if you know the total mass of the mixture, and if you know the mass of the component, the ratio of the mass of a component by total mass will also give the mass fraction, because the volume term cancels off. Okay, so we can always represent the concentration in terms of mass as well as moles, because if we know the mass, we just need to divide by the molecular weight to get the moles. So let us try to represent the concentration as on mole basis. So it is called as molar concentration, and the molar concentration is A is equal to moles of A by volume of the mixture. Instead of mass, here we are using moles of A, and we are dividing it by volume of the mixture. The unit of molar concentration is kilomole per meter cube, and it is represented by capital C suffix A. Here A represents molecules of A. Okay, similarly we can write CB and CC, which means molar concentration of B and C, and generally I can write it as CI. So like total mass concentration, total molar concentration C is equal to Ca plus Cb plus Ca, which can be written as sigma Ci. And another quantity is mole fraction. Just like mass fraction, mole fraction is equal to moles of A by total moles in the mixture, which is equivalent to for mass molar concentration of A by total molar concentration C. So mole fraction Ya is equal to Ca by C, and generally we can write Yi is equal to Ci by C for the component I. And see, all these components can be used to express concentration of either a liquid or a gas. So general convention what we use, if it is in liquid phase, we will use X to represent mole fraction, and if it is in gaseous phase, we will use Y to represent the mole fraction. So to find the rate of mass transfer, we also need to know the velocity of individual molecules inside a vessel or a medium. In a liquid or a gaseous mixture, various components will move with different velocity. So we need to know two things here. We need to know the velocity of individual components. Also, we need to know the average velocity of the medium. By this I mean average velocity of all the components present in the medium. So here I am going to introduce a term called mass average velocity. It is simply an average velocity of all the components. The representation of mass average velocity is U. Here, let's say U suffix A means velocity of A molecules alone. I somehow managed to measure the velocity at which this A molecule is moving inside the vessel. All the A molecules will have a same velocity. Let's say this is with reference to kinetic theory. So similarly, I know the velocity ub of B alone. Similarly, UC and rho A, rho B, and rho C are the mass concentrations of the different components. So if we know these things, we can define mass over velocity U as rho A UA plus rho B UB plus rho C UC by rho A plus rho B plus rho C. So multiply the mass concentration with velocity and sum up, divide by the total mass concentration. So let us, this I can write as sigma I is equal to 1 to u rho I ui by sigma rho I. Sigma rho I means rho A plus rho B plus rho C is equal to total mass concentration here, and in numerator we have rho I dui. So if you look at the units, so rho I will be kilogram per meter cube, velocity unit will be meter per second, divided by rho I again, that is kilogram per meter cube. So this kilogram per meter cube cancels off and we have the velocity, I mean unit of velocity, that is meter per second. So this is mass average velocity. So we can also find another velocity known as molar average velocity. So this is similar to mass average velocity. So to find this velocity, we will use molar concentration instead of mass concentration. So similarly, we can multiply mass concentration with individual velocities, that is CAUA plus CBUB plus CCUC by CA plus CB plus CC. So finally, we will get this expression can be written as sigma I is equal to 1 to n CIUI by C, where UA, UB and UC are individual velocities and CA, CB, CC are the concentrations of molar concentrations, and we get a quantity known as molar average velocity. The reason we need to find the molar and mass average velocities is because, see, the molecules are in constant random motion. Only if the velocity of the individual molecules are greater than the average velocity of the medium, then only these molecules will be able to diffuse out of the system. So if you want to diffuse from this vessel into some place else, then the velocity, component velocity should be greater than the average velocities. I will discuss regarding this in detail later. Now I am going to introduce another concept known as flux. Here we can say either mass flux or molar flux. So generally flux in mass transfer means mass or moles diffusing per unit area per unit time. That means it is simply the rate at which molecules are diffusing per unit area. So the question comes, what area are we talking about? So this example will make everything clear. Let's say this is a tube, cylindric rectangular tube, and which is in which molecules of A and B are diffusing. You can see molecules A, molecules of B shown by red and green, and they are diffusing in this x direction, and like you see here. Let's say the mass concentration of A is rho A, and the velocity at which it is moving is UA, and these molecules are moving through a cross-sectional area A. This area A here represents the area perpendicular to the direction in which molecules are moving. So what I want to do is I want to know the rate at which the molecules are diffusing through this particular area. So we can define flux in two ways. That is, one is mass flux, other is molar flux. Depending on whether we use mass concentration or molar concentration. So I'll start with mass flux. Here mass flux means mass diffusing per unit area per unit time. So the unit is kilogram per meter square second. So mass flux is generally represented as Na, and Na is equal to rho A into Ua, where rho A is the mass concentration of A, Ua is the velocity at which the molecule A is moving. So Na, let's take a look at the unit. The unit of mass concentration is kilogram per meter cube into Ua. The velocity is meter per second. So we will get the meter cancels off, and I get kilogram per meter square. Similarly, we have molar flux. Here molar flux, the unit is kilomole per meter cube. So we can get molar flux, which is represented by capital Na. These notations are very important. These are the standard notations. So capital Na means molar flux, which is equal to Ca into Ua, where Ca is the molar concentration of A, and Ua is the individual velocity or velocity of A in the rectangular tube. So similarly, we get the unit here as kilomole per meter square second. So Na is equal to rho A into Ua. Similarly, if we generalize, it can be written as Ni is equal to rho I into Ui. So these are the two ways in which we will represent the mass transfer through any medium. So ultimately you need to remember this: in order to get the mass flux, multiply mass concentration with the velocity of a component, and similarly to get molar flux, multiply molar concentration with the velocity. Now I'm going to introduce a tricky part which is very confusing, but I'll try to explain it in a very easy way. So let us say where there is a rectangular tube and it is composed of A and B molecules. Both the molecules are moving in x direction. Let's say A and B are moving in x direction, but with different velocities. So let's say I'm looking from outside. This is a glass tube and I'm able to see the molecules. I'm looking from outside. Here the molecules A will be moving with the velocity UA. Molecules B will be moving with the velocity UB. So there are different velocities. So I can find two quantities here. I can find molar, one is mass average velocity small u, and other is molar average velocity capital U. To understand this, think of it like this way. Let's say you are moving in a car at a velocity 60 km per hour. Another car is coming behind from you, which is moving at a speed of 80 km per hour. So for a person standing in on the side of the road, the velocity of the individual cars will be 60 km per hour and 80 km per hour. But if you are sitting inside, let's say you are sitting in a car, you are sitting in one of the cars, and you are moving at 60 km per hour, and another car is overtaking you at a speed of 80 km per hour. So what will be the relative speed at which the next car will be overtaking you? It will be the difference of the two speeds, right? So you will actually feel the speed of the overtaking car as 20 km per hour because you are also moving. So the similar thing I'm going to introduce here. Now I'm going to assume that I have somehow managed to get inside this tube, and I am moving with the velocity equivalent to mass average velocity of the molecules present here. That means the mass average velocity of the system. So then what will be the speed of A relative to mass average velocity? So the speed of A molecules, the velocity of A molecules UA relative to mass average velocity will be UI minus U. The case is I assumed I am also moving inside the vessel at the velocity equal to mass average velocity of the system. Similarly, if I travel with the mass average, if I somehow manage to get inside the vessel and I am moving with the velocity equal to molar average velocity of the system, then what will be the velocity of velocity of A molecule relative to molar average velocity, or what will be the velocity of A that I will experience? It will be Ui minus capital U, because here Ua is the velocity of A when I look at it from outside, and U is the average molar average mass average velocity of the system. Capital U is the molar average velocity of the system. So here Ui minus U is the velocity of A relative to mass average velocity, and Ui minus capital U is the velocity of A relative to molar average velocity.